Hello, everyone. So last time we started number theory, if you remember, and we looked at a few things. For example, division algorithm. So that was maybe the most important thing we proved last time. Division algorithm, which we proved using well-ordering principle, if you remember. And we also defined so division algorithm and prime numbers. So we define prime numbers, the numbers that whose only divisors are the number itself and 1. For example, 2, 3, 5, 7, and so on. And we also saw an algorithm to determine whether a given number is prime or not. So this one, we saw that, it's enough if we look at only the square root of the number and only the prime numbers up to square root of a number. If none of those numbers are divisors for the original number, then the original number must be prime. So for example, let's say I have a number 110. So normally you may think that you have to check whether 110 is even number, so it's obvious that it's not prime. But for example, 113. So normally to check 113 is prime or no, you have to check whether it has a divisor other than 1 and itself. So that means you have to check all the numbers from all the prime numbers from 1 to 113 to see whether any of those is a divisor for 113 or no. But the algorithm says it's enough if you look at the square root of the number, square root of 113, which would be, for example, less than 11, 10 point something. And only the prime numbers up to square root of it. So only prime numbers less than or equal to 10. And we have only few of them, 2, 3, 5, 7. And if none of these numbers is a divisor for the original number, then the original number must be a prime. Okay, now we want to look at the number of primes. How many primes do we have? So question, do we have infinite number of primes? And the answer to this is yes. So theorem, there are infinite number of primes. Okay. So let's see how we can prove this theorem. So proof by contradiction. So we want to show there are infinite number of primes. So if you want to use proof by contradiction, in proof by contradiction, we have to assume what we want to show is wrong. So if what we want to show is wrong, then that means there are finitely many primes because we want to show there are infinite number of primes. So suppose that there are there are finite number of primes. Say, for example, P1 to Pk. Okay, so these are all the primes that we have. Now, I want to reach a contradiction, of course. And to do that, I want to construct a number which is not divisible by any of the primes. Because by fundamental theorem of arithmetic we know that every number can be factorized into primes. So every number must be either prime itself or divisible by at least one prime. So in any case, we know that every number has to be divisible by at least one prime number. So if I can construct a number which is not divisible by any primes, then that will be my contradiction. Now the number that we are looking for will be, so consider n equals p1 times p2 times pk plus 1. Product of the prime numbers that we have plus 1. So my claim is none of p1 to pk divides n. So if we can show this, then that means, because remember P1 to PK, I'm assuming that these are all my primes, right? So I'm assuming there are finitely many primes and I'm calling them P1 to PK. So according to my assumption, there is no other prime number other than P1 to PK in the world. So these are all the prime numbers in the world, P1 to PK. So if none of these divides n, that means n is not divisible by any prime numbers, and that will be my contradiction. So why none of these divides n? So if not, for example, pi will divide n for some I between 1 to k. Then, okay, so see, look at here. So pi divides n by my assumption. Of course, pi divides p1 times p2 times pk as well, right? Because remember, pi is one of, I is one of the numbers in 1 to k. So pi is one of the numbers p1, p2 to pk. Now, if pi divides n and pi divides p1 times to pk, pi will divide the difference between these two. And so pi will divide n minus p1, p2 to pk. But what is the value of n? Look at this, the first equation I wrote. N minus p1, p2 to pk is simply 1, right? Because n is p1 times to pk plus 1. So that means pi divides 1, which is not possible. Pi is a prime number, right? It cannot divide 1. Remember, a divides b means a is a factor for b. So 1 has no factor other than 1 itself, right? So pi is a prime number, cannot be a factor for 1. So what does that mean? So that means none of pi's. So our claim, the claim is proved. Claim is proved, which means none of pi's divides n. And this is a contradiction. Since, why is the contradiction? Because, well, we know that by fundamental theorem of arithmetic, n must have at least one prime factor, but none of the prime numbers in the world divides n. So n, since n has no prime factor, but it must have at least one prime factor, according to fundamental theorem of arithmetic. Fundamental theorem of arithmetic said that every number must have at least one prime factor. It's either a prime itself or it's factorizable into primes. And in any case, it will have at least one prime factor. Okay. So there are infinitely many primes, but let's say if we have a fixed number n, how many prime numbers do we have up to that point? That's another question. For example, let's say up to 1,000. How many prime numbers do you think we have? Do we have, for example, square root of 1,000 prime numbers? So the question, let me state the question. So another question. Fix a positive integer n. How many, or let's say approximately, because of course we cannot expect to have the exact number of prime numbers. So approximately, how many prime numbers do we have which are less than or equal to n? So for example, 10,000, if n is equal to 10,000, approximately how many prime numbers do we have which are less than or equal to 10,000? Do you think, for example, square root of 10,000? Or maybe you think 10,000 to power 1/4, or maybe logarithm of 10,000. Approximately how many prime numbers do we have? So this is called, it has a name, this function that counts the number of prime numbers less than or equal to a fixed number. It's called pi of x. Okay, so let's give a definition here. Given an integer n, pi of n denotes the number of primes which are less than or equal to n. So for example, let's say pi of 10 is equal to number of primes which are less than or equal to 10. And how many primes do we have that are less than or equal to 10? So that means number of elements in the set 2, 3, 5, 7. These are the only primes that are less than or equal to 10. How many of them, therefore, do we have? Because it's the pi of a number is number of primes that are less than or equal to 10, or less than or equal to the given number. In this case, it's 10. So number of elements in the set 2, 3, 5, which is 4. Okay, so pi of x. Now we want to know the behavior of pi of x. How does it grow? Like I said, is it, for example, the pi of a number means number of prime numbers less than or equal to that number? How many prime numbers do we have? Is it square root of the given number? Is it fourth root of a given number? What is it? Is it logarithm of the given number? Now there is a theorem, very famous theorem in number theory called prime number theorem. Prime number theorem determines the growth of pi of x as x goes to infinity. So prime number theorem says that with notation above, we can say that limit pi of x divided by x over ln x as x goes to infinity is equal to 1. In other words, as x goes to infinity, the growth of pi of x is similar to the growth of x over ln x. So if I want to describe this simply, this means the number of primes, as if x is very large, number of primes less than or equal to x is relatively large. Because what is the maximum for pi of x? The maximum number of primes is x itself, right? So for example, let's say if x was 10,000. At most, how many primes do we have less than or equal to 10,000? Of course, 10,000 itself. And of course, we know that 10,000 cannot happen, meaning that not all numbers between 1 to 10,000 are primes, right? So if all numbers between 1 to 10,000 were prime, then number of primes would be 10,000. But of course, that's not the case. We have many numbers which are not prime. For example, 2, 3 are prime, then 4 is not prime, 5 is prime, 6 again not prime, 7 prime, 8 non-prime, 9 not prime, 10 non-prime, and so on. So of course it's less than 10,000, number of primes less than or equal to 10,000. But how much less? Like I said, can we say maybe square root of 10,000 is the actual number? No, the prime number theorem says x over ln x is an approximation for pi of x, for number of primes less than or equal to x. So for example, in the case of 10,000, 10,000 over ln 10,000 is how much? Pi of 10,000, you can say almost equal to 10,000 over ln 10,000. So ln 10, so let me tell you how much is this number. $10,000 over ln. So this is 1,000, almost 1,085, which is a relatively large number, you know. Among the first 10,000 numbers, almost 1,000 of it are all prime. Now, if x goes bigger and bigger, you know, x over ln x behaves more like x, right? Because ln x, x over ln x means x divided by some number, right? Now, ln x is relatively small compared to x. So we are dividing x by a small number, right? So which means overall we have relatively large number. So for example, if you want to compare x over ln x versus root x, even root x is big, right? If, for example, if I knew that I would have root 10,000 numbers, root 10,000 prime numbers less than or equal to 10,000 still is a relatively large number. But which one is bigger, this one compared to this one? You can show that this one is bigger, right? Meaning that the ratio of this divided by this goes to infinity as x goes to infinity. So this is a bigger number. So x over ln x. So this is called asymptotic behavior. So in advanced mathematics, in more advanced mathematics, different branches, one topic is to determine asymptotic behavior of some, objects under study. So asymptotic behavior means as x goes to infinity, what happens? Now, pi of x, the asymptotic behavior of pi of x is that it's similar to x over ln x, which means the number of primes less than or equal to x is relatively large. It's almost x just divided by some small number, which is ln x. Okay, this is a deep theorem in advanced mathematics and advanced number theory. And we actually don't need the proof for this in this course. So I think this much is enough. It's about the number of primes less than or equal to x. Now let's look at the next topic. Okay, let me just keep the sentence that I said about 10,000. Pi of 10,000 almost equal to 10,000 divided by ln 10,000, which is almost equal to 1,085. Okay, so now the next topic is a greatest common divisor. And least common multiple. So definition, given two numbers or two integers, a and b, let d be the largest integer such that d divides a and d divides b. This integer d is called the greatest common divisor of a and b. Common divisor of a and b, denoted by GCD of a and b. Similarly, let L be an integer. So let's say let L be the smallest integer such that A divides L and B divides L. Okay. This number L, or this integer L, is called the least common multiple of A and B, denoted by LCM of A and B. Okay, so these are the definitions for GCD and LCM, greatest common divisor and least common multiple of two integers. So let's look at an example. Let's say, for example, A equals 20, B equals 30. Find GCD of A and B and LCM of A and B. So for GCD of A and B, let's look at the common multiples of divisors of A and B. Common divisors of A and B. What are the divisors of A and B? So let's look at divisors of A. Divisors of A, divisors of 20, of course, is 1. And then 2, right? What else? 4, 5, 10, and 20. Divisors of B, which is 30, are 1, 2, 3, 5, 6, 10, and 15, and 30. So these are the divisors of A and B. Now we are looking for greatest common divisor. So first look at the common divisors. What are the common divisors? So these are, 1 is a common divisor. 2 is also a common divisor. Common means a divisor for both numbers. So 1 is a divisor for both, 2 is divisor for both, 5 is divisor for both, and 10 is also divisor for both. So these are the common divisors. So these 4 numbers are common divisors. And which one is the greatest one? Which one is the biggest among these 4? The biggest number is 10. So that means greatest common divisor is 10, right? Between 1, 2, 5, and 10, the greatest one is 10. So that means GCD of 20 and 30 is 10. Similarly for LCM, so let's list the multiples first. So multiples of A, multiples of 20 is 20 itself. A was 20, right? So 20 itself, 40, 60, 80, 100, 120, and so on. And multiples of B, multiples of 30, 30, 60, 90, 120, and so on. Then we need to look at the common multiples. Remember, we're looking for least common multiple. So then you have to look at the common multiples. So common multiple, 60 is a common multiple. 120 is a common multiple. And so on. So the least common multiple will be least common multiple is 60. Okay. So, or in other words, LCM of 20 and 30, 60. All right, so this one, we could find GCD and LCM because the numbers were small, and we could find GCD and LCM by just investigation. But can we find a recipe or a general algorithm, to find GCD and LCM in general case? So an algorithm to find GCD of A and B and LCM of A and B. So first we need a factorization. First, factorize A and B into prime factors, prime numbers. So let's say A equals P1 to power N1, P2 to power N2 to Pk to power Nk, and B equals P1 to power M1, P2 to power M2, all the way to Pk to power Mk. So here you could ask me a question or an objection that why did I list same prime numbers that I listed for A, which I call them P1 to Pk, I listed the same prime numbers P1 to Pk for B as well. Am I allowed to do that? Because of course it's possible that the prime numbers that are listed for A are different than the prime numbers that are listed for B. For example, let's say if A is 10, then this is 2 times 5, but if B is, for example, 9, then it's 3 to power 2. So this prime number is not same as these prime numbers. So I wrote the powers different, and as you can see, the powers are different. The powers are 1 and 1, and this one 2, but the prime numbers could be also different. Why do you think that I listed the same prime numbers, and under which circumstances I'm allowed to do that? I'm allowed to assume the same prime numbers appear for A and B. The answer is yes. In general, I'm not allowed to assume the same prime numbers that appear for A, the same prime numbers appear for B, but I'm allowed to assume that under one certain condition. And that condition is that if I assume that the powers of these prime numbers are allowed to be 0, then I can assume this. Because see, for example, look at 10. 10 was 2 times 5, 9 was 3 to power 2, right? If I allow power 0 for my prime numbers, then I can consider the set of all prime numbers that appeared either here or here, which means 2, 5, and 3. So then I can write 10 as 2 times 5 times 3 to power 0, and 9 as 2 to power 0 times 5 to power 0 times 3 to power 2. Right? Now see these numbers, 253, 253. I can write it in this form because I allow power 0 for my prime numbers. Okay, so here I have to mention that where P1 to Pk are all prime numbers, right? So just have this example in mind so that we know what to write here. Are all prime numbers that appear either in prime factorization of A or prime factorization of B. B and the powers Ni and Mi above are non-negative integers. Let me just, as an example, give you this example so that when you read it, you understand better that, for example, if A is 10, which is 2 times 5, B is 9, which is 3 to the power 2, then I can say A is 2 times 5 times 3 to the power 0. B is 2 to the power 0 times 5 to the power 0 times 3 to the power 2. So this is like my P1, this is my P2, and this is my P3. Okay. So then, so remember I'm trying to give an algorithm or recipe to find GCD and LCM of two numbers. So the very first thing that you should do to find GCD and LCM in this method, first factorize them into prime factors, each one to some power. Then I want to tell you what GCD and LCM would be. Then GCD of A and B is equal to P1 to power minimum of N1 and M1 times P2 to power minimum N2 and M2 all the way to Pk to power minimum Nk and Mk. And similarly, LCM of A and B is equal to P1 to power maximum N1 M1 all the way to Pk to power maximum Nk Mk. Now let's see whether we can prove this proof for GCD. Let me call this one maybe formula 1 and this one formula 2. Let me say proof of 1. So I want to show that this expression that is appeared in the right-hand side is GCD of A and B. GCD means greatest common divisor. So first of all, I have to show that this is a common divisor for A and B. And then show that this is greatest common divisor for A and B. So first, we show that. So let me call it maybe D equals P1 to power minimum N1 M1 all the way to Pk to power minimum Nk Mk is a common divisor of A and B. So what is a common divisor? So that means I have to show that it's a divisor of A and is also a divisor of B. Now let's look at A. What is A? A is P1 to power N1 all the way to Pk to power Nk. If I want to show that one number is a divisor of another one or is a factor of another one, How can I do that? I have to write the second number as the first number times some other number, right? So for example, you want to show 5 is a factor of 10. How would you do that? You can write 10 as 5 times another number, which is 2 in that case. And then that means 5 is a factor of 2, or 5 divides, 5 is a factor of 10, or 5 divides 10. So here, if I want to show that D is a divisor or a factor of A, I have to write A as D times some other number. And then that means D is a divisor of A. So A equals, okay, it seems that the screen is freezed. Maybe I can stop share. Let's share again. So A equals P1 to power N1 all the way to Pk to power Nk. Now I want to write it as D times something. So P1 to power minimum N1 M1 all the way to Pk to power minimum Nk Mk, which is my D times, okay, times which number would give me A? P1 to power. So I need P1 to power N1 as a result. And right now I have P1 to power minimum N1 M1. I have to multiply this with which number to get P1 to power N1? I have to multiply with P1 to power N1 minus minimum N1 M1 times all the way to Pk to power Nk minus minimum Nk Mk. Right? P1 to power minimum N1 M1 times P1 to power N1 minus minimum N1 M1 would give me P1 to power N1. Similarly, all the way to Pk to power Nk. I can also mention here, note that Ni minus minimum Ni is bigger than or equal to 0. So please note that I need all the powers to be non-negative, because if a power is negative, then I don't have an integer anymore. In number theory, we are dealing with integers, right? So all these concepts, factors, divisors, were for integers. So if I can write my number A as D times some integer, then that means D divides A. But if I write A as D times some non-integer or some fraction, then it doesn't mean that D divides A. So I need all numbers to be integer, which means all powers to be non-negative. Now, what are the powers of my, so if you look at A, this is number A, and I have a number D appeared times this number, which I need it to be integer, and that means I need the powers to be non-negative. What are the powers? Powers of the form Ni minus minimum Ni Mi, which is always non-negative. Why? Because minimum of two numbers is less than or equal to both numbers, right? So minimum Ni and Mi is of course less than or equal to Ni. Therefore, Ni minus minimum is non-negative. So that means D divides. So D was, you remember what I mean by D, right? So D, which I defined it as P1 to power minimum N1 M1 times Pk to power minimum Nk Mk and divides A. Similarly, one can show that D divides B. So we showed that D divides both A and B. We showed D is a common divisor of A and B. Now I want to show this is greatest common divisor. So to show D is GCD of A and B, let D2 be a common divisor of A and B. So what does that mean? That means D2 divides A and D2 divides B. Now claim is D2 can be written as P1 to power, let's say, S1 times P2 to power S2 all the way to Pk to power Sk, where Si is less than equal to minimum NIMI for each I between 1 to K. So I want to show that D is the greatest common divisor between for A and B. So for to show this, I considered a common divisor between A and B. I called it D2. So if D2 is a common divisor of A and B, that means D2 divides both A and also B, right? Meaning that D2 is a factor of A and also is a factor of B. Now my claim is that D2 can be written of this from P1 to power S1 all the way to Pk to power Sk. And each Si is less than or equal to minimum NIMI. So of course I have to prove the claim. But once I prove the claim, I will be done. Why? So let me tell you, I'll prove the claim in a few minutes, but once I prove the claim, why am I done? So once the claim is proved, what can we say? Then we can say that D, which is P1 to power minimum, N1, M1, all the way to Pk to power minimum, Nk, Mk, is equal to D2 times P1 to power minimum N1 M1 minus S1 all the way to Pk to power minimum Nk Mk minus Sk and that means D2 divides D so let me see the screen is freezed. Maybe I can stop share again. So D, we can write it as D2 times some number, which means D2 divides D, right? So please note that once the claim is proved, I know that each SI is less than or equal to minimum NIMI. So that means each of these powers here again are all non-negative. Therefore, D2 is, therefore this number is an integer. The powers are non-negative. So D2 times an integer is D. That means D2 divides D, or D2 is a factor of D. Now, what does that mean? So that means D is bigger than or equal to D2. D and D2 are both positive numbers, right? And D2 is a factor of D. So that means if I have two positive numbers, the first is factor of second. So second is bigger than or equal to the first, right? So for example, 5 is a factor of 10 and 10 is bigger than or equal to 5. And that means D is GCD of A and B. So if D is bigger than or equal to D2, what was D2? D2 was any common divisor of A and B. If D is bigger than or equal to any common divisor of A and B, well, that means D is greatest common divisor of A and B. So it only remains to prove the claim, proof of claim above. So what was the claim? That if I have a common divisor D2 for A and B, D2 can be written of this from P1 to power S1 all the way to Pk to power Sk. Okay, first of all, in D2, these prime numbers must appear. We cannot have any prime numbers other than P1 to Pk, which were the prime numbers appeared originally for A and B, appear in D2. Why? Because, for example, if some other prime numbers, such as, for example, Q appears in D2, and Q is not any of P1 to Pk, then what would happen? So first, note no prime number other than P1 to Pk can appear in prime factorization of D2. If not, say, for example, D2 is equal to Q to some power S, let's say, right, times, let's say, P1 to power S1, Pk to power Sk, with Q not equal to P1 and Q not equal to Pk, and S bigger than or equal to 1. So if some other prime number appears for D2, then this will not be possible. Why? Because if you look at D2, what do we have? We know that D2 divides both A and B. We have D2 divides A, so that means A is equal to D2 times, let's say, some number A prime, for example. So A, what was A? P1 to power N1 times Pk to power Nk. If you look at the original notation we used for A, this was it. And then D2 is Q to power S, P1 to power S1, Pk to power Sk times some number A prime. Now this right-hand side Q divides this number. But Q does not divide this number, because none of these PIs is same as Q. So then this equation cannot hold. Right? The left-hand side is not divisible by prime number Q. Right-hand side is divisible by prime number Q. So these two cannot be equal, which means that in the prime factorization of D2, I cannot have any number other than P1 to Pk appear. So that means D2 in the prime factorization, only P1 to Pk can appear. Each one to some power, let's say S1 to Sk. Now, my second part of claim was that each of these powers must be less than or equal to the minimum NIMI. So this part we can prove by contradiction. It remains to show Si bigger than or equal to, Si less than or equal to minimum and IMI for every I between 1 to k. If not, again, let's say Sj bigger than minimum and JMJ for some J. So what does that mean? That means Sj is bigger than Nj or Sj bigger than Mj. Right? If a number is bigger than minimum of two numbers, it's bigger than at least one of them. So if Sj is bigger than Nj, then I can say that D2, which is P1 to power S1 to P1, Pj to power Sj, Pk to power Nk, Sk will not divide P1 to power N1 times Pk to power N, Pj to power Nj, Pk to power Nk, which is my A, because power of Pj is Sj, which is bigger than power of Pj in A. Power of Pj in Sj in factorization of D2. And this is bigger than power of Pj in factorization of A. And therefore D2 will not divide A because it has a bigger power here for Pj compared to here. So this cannot be a factor of this, right? For example, 5 to power 3 cannot be a factor of 5 to power 2, right? 5 to power 2 is a factor of 5 to power 3, but 5 to power 3 cannot be a factor of 5 to power 2. So this is not possible because remember we were assuming that D2 divides both A and B, is a common divisor of A and B. Similarly, Sj divide bigger than Mj is not possible either. So that's it. So that means, every Si is bigger than, less than equal to minimum and IMI. Okay. So that's it. So we showed that. Hence, D is equal to P1 to power minimum N1 M1 all the way to Pk to power minimum Nk Mk is GCD of A and B. So note here, important remark, the proof above shows that if D2 is a common divisor of A and B, then D2 will divide D, which is GCD of A and B. So by definition of GCD, we know that GCD is the greatest common divisor. Therefore, GCD must be bigger than or equal to any common divisor, which I called it D2. But the proof showed that not only D is bigger than or equal to D2, D2 is a factor of D actually. This is actually the way that we showed that D is bigger than or equal to D2, remember? Let me show you here. Here, look at the first line here. I showed that in order to show that D is bigger than or equal to D2, first I show that D2 is a factor of D. What was D2? What is D? D2 is an arbitrary common divisor for A and B. D is the greatest common divisor for A and B. So any common divisor of A and B, called D2 here, is a factor of the greatest common divisor, which is denoted by D here. So that's why I said the proof shows that if we have a common divisor of A and B, the common divisor is always a factor of the greatest common divisor. So this was the proof of, remember we had two parts for GCD and LCM. I did the proof for GCD. Now you can do the proof of LCM as an exercise. So proof of LCM, proof of 2, the formula for LCM, exercise. And once you do the proof, you will see that a similar version of this remark will hold for LCM. So remark, the LCM has the following property. That if, let's say, A divides, let's say, for example, L2, and B divides L2, i.e., if L2 is a common multiple of A and B, then what happens here? I'm writing the corresponding property of this remark, which was about GCD, the corresponding version for LCM. The GCD version said that if you have a common divisor of A and B, then the common divisor divides or is a factor of the greatest common divisor. Now, what do you think the corresponding version would be for LCM? For LCM, we would have, instead of having D2, which was a common divisor, here we have L2, which is a common multiple. And a common multiple of A and B means if A divides L2 and B divides L2, then what can I say? Then L, the least common multiple, will divide L2. In the case of great GCD, because D was the greatest common divisor, arbitrary common divisor was a factor of D. But now this is the opposite situation. Now here L is the least common multiple. So an arbitrary common multiple. So L is a factor of an arbitrary common multiple. So normally, if you have one number divides the other one, this number here is less than this number, right? So this is one way. Let me tell you one way to remember this property. For example, think about 5 and 10. 5 divides 10, 5 is less than 10. Now, in the case of GCD, D was the greatest common divisor, D2 was less than that. So therefore, D2 was dividing this. I'm just telling you a way to remember. Of course, it's not obvious why D2 must divide D. Well, it's obvious that D is bigger than D2. But why can we say D2 is a factor of D? Well, the proof, a part of proof showed this property. But so we proved this as a part of proof, but one way to remember was that D is the greatest common divisor, so it must be bigger than D2. So that's why we say D2 is a factor of this. However, here, L is the least common multiple. L is the least common. L2 is an arbitrary common multiple. So L has to be less than L2. Therefore, we say L is a factor of L2. Again, it's not obvious. Well, the fact that L has to be less than L2 is obvious according to the definition of least common multiple. But why can we say L is a factor of L2? Again, if you look at if you write the proof as an exercise, you'll see that as a part of proof, you can see that, or you can show that L is a factor of L2. Not only is less than L2, less than equal to L2, but it's also a factor of L2. Okay, so I'll give you examples. So let's look at an example.